Hello friends, you are watching ERUDIRE Plus, the professional CAD/CAM solution provider. Let's get started.
Hello viewers, this is the second finite element problem of vibration, and in this case we'll be using fixed beam. To that it will be a lumped mass at a specific location. We'll provide a specific lumped mass and we have to find out the natural frequencies. By the same time we'll have to see the mode shapes. Let us see the problem, what it is talking about. A shaft fixed at both the ends has a mass of 120 kg placed at a distance of 250 mm from left hand side, and we have to determine the frequency of the natural transverse vibrations. Length of the shaft is 700 mm, and it is provided that modulus of elasticity of this material equal to 200 gigapascal. And also we have to compare the results with theoretical calculations or theoretical value, right? This is clear. It is a fixed beam, both sides is fixed. It is having diameter of 40 mm, and at a specific location from left hand side the distance is 0.25 meter away. We have provided a lumped mass and we need to find out the frequency of natural transverse vibrations, and also that to be compared with theoretical calculations, right? So without wasting time, let us start our analysis using ANSYS mechanical APDL. After that we'll compare the results with theoretical calculations also, right? Let us go back to ANSYS mechanical APDL. So first of all we need to change the directory, and we can change it to any locations, right? And next to that we need to change title of this one, right? That we started from file, change title, and we can rename this one as FA2. Okay, to view the title we can start with plot replot, and it will be visible at the lower left corner. FA2 is visible, and as per normal practice we need to start from preferences. We need to select what type of analysis it is. It is a structural analysis. So next one, we need to select elements or elemental properties. It will be starting from preprocessors. Preprocessor, element type, add, edit, delete. Nothing is defined, so we need to add it. We're considering beam element with 3D finite strain. Apply. We need to select another mass because two different masses will be there. One will be lumped mass having mass of 120 kg, and another will be shaft of diameter 40 mm. So second one we can select structural mass. Okay, and we can provide the properties of this one. We can see the options of beam 188, and elemental behavior it will be cubic form. Similarly for the second one, for mass 21, let us see the options, and we are considering this one as 2D rotational. Okay, close it. It is done. Next to that you need to provide real constants to provide the value for the lumped mass. So real constants, add, edit, delete. We have to add it, and for the lumped mass we need to provide the specific value of that. So let us provide that value of this one as 120 kg. Okay, close. Lumped mass is provided. Next to that you need to provide material properties. Material properties, material models, structural, linear, elastic, and isotropic. Isotropic means material property remains same in all directions. So modulus of elasticity of this one is 2E11. 2 into 10 to the 11 Newton per meter square, and Poisson's ratio is 0.3. Okay, density you can provide 7800 kg per meter cube. Okay, so material property is provided. Next to that we need to select sections. What type of section it is? It is a circular cross sections. So sections, the beam is having circular cross section of diameter 40 mm. So sections, beam common sections. From subtype we can select the cross section. It is a circular one, and diameter is actually 40 mm, so we can provide radius equal to 20 millimeter, that is 0.02 meter. Okay, done. Next to that, we need to start with modeling. And in this case, it will be better to create nodes, because if we are creating nodes, in that case meshing is not required. We can remember the beam is having length of 0.7 meter, and at a distance of 0.25 meter from left hand side we are providing a lumped mass, right? We need to create 3 different nodes, and in between 3 different nodes 2 elements will be there, right? So we are creating nodes. Create nodes in active coordinate system, and first node by default it will be created at origin, so we are not providing that default values. It will take the default value of origin. Apply. First node is created at origin. Second node will be created at a distance of 0.25 meter from left hand side. 0.25 meter from left hand side. Apply. Second node is also created. Now the last node will be created at a distance of 0.7 meter. Okay, so 3 nodes have been created. Now all these 3 nodes need to be joined in the form of an element, right? So what we do is we can create elements auto numbered through nodes. First node select, second node select, apply. First element is made. Now the second node and third nodes are selected. Okay, so 2 elements are made. In between first node and second node we are having first element. In between second node and third node we are having second element. And at node number 2 we will be providing a lumped mass of 120 kg, and both left hand side and right hand side will be fixed. It is a fixed beam, right? Next to that we need to provide that lumped mass at location 2, that will be provided from elemental attributes. So element attributes, and we can select element type. The shaft is actually beam 188, and for selecting that lumped mass we need to select mass 21, right? You can see, done. We are selecting mass 21. Okay, through nodes we need to select that location. So at node 2 we are providing lumped mass of 120 kg, right? Okay, done. Next to that we need to provide some boundary conditions. That means the left hand side and right hand side should be fixed. So meshing is not required because we have already provided nodes. Now we're starting with solution, analysis type, new analysis. It is a modal analysis. So next to that we need to select analysis options, and default it is block Lanca's method. Here we are considering PCG Lanca's, and numbers of modes to extract equal to only 1, and we are expanding only one mode. Okay, next to that we are considering the default setup. Okay, now we need to apply our boundary conditions. That means the left hand side and right hand side should be fixed. So it will be coming from loads, apply structural displacement on nodes. Let us select node 1 and the last one. Okay, and all degrees of freedom we are providing 0 values. That means the first node and the last node will be having 0 displacement, that is having no displacement. We are not providing 0 value because by default it will take 0 value. Okay, so the first node and the last node is fixed, it cannot move. It is a beam of diameter 40 millimeter. The left hand side and right hand side is fixed, and from the left hand side at a distance of 0.25 meter we have provided a lumped mass of 120 kg at node number 2, right? So everything's done. Now we can run it. Solve, current ls. Okay, solution is done. Now we can see our results from general post processing. Result summary. You can see the result is 60.033. So frequency is 60.033, right? This is our result. We can save it. We can save it anywhere else, specific locations. 60.033 is the result. Okay, done. We can see the mode shapes also. Let us see the mode shapes. Read results, first set, plot results, and deform shape. Deform plus and deform, that will show the mode shapes. This is the mode shape, right? And from left hand side, at a distance of 250 mm, we have provided a lumped mass of 120 kg. This is the mode shapes. We can see list results. List results, nodal solution, y component of displacement. You can see maximum displacement is occurring at node number 2, 0.9017 into 10 to the minus 1. We can save this one and let us close it. Let us see the animation of this one. Let's see how it is animating. We can make the animation faster by reducing the delay period. So this is the vibration of that fixed beam, which is having a lumped mass of 120 kg at a specific distance of 250 mm from left hand side, right? Let us stop it. Next to that, we need to validate these results using theoretical calculations. Before that, we can see our results again. From result summary, you can see that frequency is 60.033, right? That to be validated using theoretical calculations. So let us close it. So this was the problem. A fixed beam is having a lumped mass at a distance of 0.25 meter from the left hand side, and our task is to find out the natural frequency of this one, and that should be validated with theoretical calculations, right? Let us see the next slide. See, for lumped mass systems, we are having frequency equal to 1 upon twice pi and square root of g upon delta. So here delta is actually deflection, and for different boundary conditions we'll be having different deltas. And for cantilever beams, delta equal to mgl cube divided by 3ei, and for simply supported beam it is mg a square b square divided by 3eil, and for fixed beams it is mg a cube b cube divided by 3eil cube. So in this case we can see that m equal to mass, g is acceleration due to gravity, l is length of the beam, a is modulus of elasticity, and I equal to moment of inertia. But what about a and b? We can go back to the previous drawing and see what is a and b. So in this case, a is actually when the mass is at a distance of 0.25 meter. So this part is equal to a and this part is equal to b, right? So a is equal to 0.25 and b equal to 0.7 minus 0.25. b will be equal to 0.45, right? Okay, now we need to calculate this one. So while calculating these things, we have to find out frequency. Like in our case, as the beam is fixed at both the ends, so delta will be this one. We have to follow this equation, delta equal to that. We can have a box and we can see our formula that we used for our calculations. We need to apply this equation to have our frequency. First delta to be calculated and this delta to be applied in the equation of frequency here itself. Right, but the actual formula will be a little bit of tricky one. Let us see that calculation how it will be. Because we are having a lumped mass, so deflection of the lumped mass will be there, by the same time deflection of the beam will be also there. We have to consider both the deflections, right? So delta 1 and delta 2 should be considered, not only single delta of the lumped mass. So the calculations, let us see it how it will be. First of all, we need to find out the value of moment of inertia of this one, because moment of inertia is not given, right? Moment of inertia can be calculated like I equals to pi d to the power 4 divided by 64. And after putting the value of diameter in this equation of moment of inertia, we will get the value of 125.663 into 10 to the power minus 9 meter to the power 4, right? Exactly same way we have to find out things like delta 1, that is a deflection of the lump mass. By the same time we have to find out deflection of the beam also, as it is a fixed beam. So delta 1, that is deflection of the lump mass, it will be delta 1, we can write deflection of the lump mass, delta 1 should be equals to mg a cube divided by 3 EIL cube. And you know that a equal to, already told, in this case a will be equal to 0.25 and b will be 0.7 minus 0.25, that is 0.45. After putting all these things, we'll get the value of delta 1 equal to 64.81 into 10 to the minus 6. You can write this one with text. It will be 64.81 into 10 to the minus 6, e minus 6. This is delta 1. Now exactly same we have to find out for delta 2. Delta 2 will be the deflection of the beam. Let us put the value of delta 2, or you can say delta s, right, of the shaft. Deflection of the shaft equal to delta s. It is given by 5 mg L to the power 4 divided by 384 EI. 5 mg L to the power 4 divided by 384 EI. And after putting all these values in this equation, we'll get delta s equal to 8.373 10 to the power minus 6. You can write this one with text. It will be 8.373 into 10 to the power minus 6, e minus 6, right? This is the value of delta 1 and delta s, deflection of the lump mass and deflection of the shaft. Now that to be added with a specific equation again. So final equation of frequency, it will be Fn. Let us drag this one this side and to put the value of frequency, right? So frequency final equation, it will be Fn equals to 1 upon twice pi square root of g by delta. So here delta will be the addition of both the deltas. It will be delta 1 and delta s both, right? So we can write this one as delta 1 and plus delta s divided by some small factor 1.27. After putting all these values, we'll get the final value of frequency equal to 58.99 Hz. And in our case, we got the result from ANSYS equal to 60.033. ANSYS, this is result from theoretical calculation, and from ANSYS we got 60.033. ANSYS result equal to, you can put the result from ANSYS. You can note this one, this is from theoretical calculations. And from ANSYS we'll be getting something else. ANSYS we got something else. And from ANSYS we got the result 60.033. 60.033. That much of Hz. So percentage error is very less. In this case it will be definitely less than 3%, which is acceptable, right? So this is all about our second analysis. In this analysis we have taken a fixed beam, and at a specific distance from the left hand side we have provided a lumped mass, and the lumped mass was having a weight of 120 kg. And in this case we have found the frequency natural transverse vibrations, and that was validated using theoretical calculations. And in both cases we got a percentage error which is less than 3%, which is acceptable, right? So with this one we'll conclude our today's analysis. Thank you so much for watching this video. Thank you again. Bye. If you like this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.